Thank you very much. Thank you for having me. Let's talk about what is the essence of software architecture, which is how to do trade-off analysis. Your job as a software architect is to not find magic silver bullet solutions to problems that are laying around, because they almost never exist. And if they did, somebody would have already found them. Your best job as a software architect is to get really, really good at doing objective trade-off analysis. Because the important decisions in your organization, they're going to look to someone who they can go to and say, okay, I really need the facts about this, not some sort of evangelization about something. I need to know what are the pluses and minuses so I can make an informed decision. That's what I'm going to be talking about this afternoon. If you look in Google analyzing trade-offs, you'll find some things like this. ATAM, which is the Architecture Trade-off Analysis Method. This was developed decades ago by the Software Engineering Institute, and its purpose was to help you do this kind of trade-off analysis, but it suffers from, well, it being 20 or 30 years old, but it also suffers from not reflecting the realities of today's architecture. In fact, here are all the steps in ATAM. Don't bother reading all these, because I'm going to mark out the ones that are no longer useful in the current day and age. Well, that really just leaves the one there. And all that's really good for is documenting your trade-offs. I came up with this clever little tree structure called an ATAM utility tree, but this assumes that how many of you have an organization that's willing to stop working for a week and have a meeting with the architects to talk about things and review their plans, and then several weeks later stop everything again for several days, and it's just never going to work. Things move way too fast to handle this in the modern world. This is a reflection of, in our book, Fundamentals of Software Architecture. As we were writing that book, we were trying to find things that seemed universally true, and we were hoping to find like 10 of them, and we found 2. And the first one of these is that everything in software architecture is a trade-off. In fact, in many ways, this sort of defines software architecture, because you can say that software architecture decisions are ones that have significant trade-offs on either side of the decision, which is what makes it a difficult decision. But there's a corollary to that law that said if you think you found something that isn't a trade-off, it just means you haven't identified what the trade-off is yet. And reuse is a great example of that, because people think that reuse is always a force for good, right? And I have organizations tell me, well, we really love the idea of highly decoupled architectures like microservices, because you can have a really fast rate of change, so we want that. But we don't want all of our teams rewriting the same stuff over and over, so we want a high degree of institutional reuse at the same time. And I have to break the news to them, well, you know, the way you implement reuse is via coupling. So you can't have a decoupled architecture and reuse, because those two things are counter to one another. That's missing the trade-off of that reuse has a negative side as well that you have to take into account. This was the only corollary we had in the first edition of this book, but we're currently feverishly working on the second edition, and we've added another corollary. You're the first audience to see the second corollary to the first law in the Fundamentals second edition, and it is, you can't avoid doing it over and over again. One of the messy things about software architecture is you can't choose one of these decisions and just make it once. We're always going to do choreography in our architecture. That's a disaster, because every time you need to figure out a workflow, you need to do the trade-off analysis again, because there are always enough things that are different that will drive you from one to the other on a case-by-case basis. We talked about this in the Fundamentals of Software Architecture book, and in Head First Software Architecture, the Head Software Architecture, the hard parts. Our most recent book is Head First Software Architecture, which Mark and I wrote with Raju Gandhi. And in the Fundamentals book, we purposely avoided a kind of a messy question, which is, what's the difference between architecture and design? because it's one of those questions that you could write an entire book about and still not say anything really that useful. And of course, we could avoid it entirely in the Hard Parts book, but Head First book is meant to be a sort of an intro book, and we felt compelled to address this question of what's the difference between architecture and design, and so we were forced to do that, and we did so. And the reason this is such a tough thing to nail down is because, like virtually everything in software architecture, this is not a binary. It exists on a spectrum. So there is no hard, this is architecture, this is design. Instead, it falls somewhere on this spectrum between architecture and design. But as soon as you realize that, you can answer the question, well, what pushes it in one direction or the other? And so Mark and I, to create interactive exercises, created a scale from A for architecture to D for design. See how nicely that worked out of the A through D letters there? So architecture decisions tend to be strategic. These are long-term strategies in our organization. We're trying to build a foundation for something, whereas design decisions tend to be more tactical. I need to solve this problem right now, and I'm going to address it with this decision. Architecture decisions are high effort, both to implement and even more to change later. If I choose microservices now and I want to change that to something else later, that's a very high effort to do that, whereas design is typically low or lower effort. User experience, I need to change the position of a button as an example of a very low effort kind of design decision. And significant trade-offs, well, I don't guess any of them are insignificant, but less significant trade-offs is another hallmark of something that's architecture versus design. And so you can ask yourself the question, when situations come up, is this really more about architecture or design? We're considering using microservices for the new system. Well, that one's pretty strongly architecture. It's strategic, it's a very high effort, and there's serious trade-offs around data fidelity and transactionality and performance, and responsiveness, et cetera. That one's pretty easy. Similarly, we need to move the cancel button to the bottom of the screen. Well, that one's clearly tactical and a lot easier. And guess what? Almost none of your decisions fall on the opposite ends of the spectrum. They're a lot more like this. We're considering breaking the single payment service into separate services, one for each payment type. Well, you could go back to philosophy here, because the philosophy of microservices says that everything is supposed to be single purpose. Okay, great. But what does that mean? Are all payments single purpose, or is each kind of payment single purpose? Because I could argue over drinks for either one of those positions and more or less be correct. So philosophy is a terrible way to make this decision. What we need to do is some trade-offs. And we're going to look at this exact problem in just a bit as to how to do trade-off analysis to solve this particular little problem. One of the questions that we often get is, well, you know, in the design world, they don't talk about things like evolution. They talk about emergent design. Why can't we do that in architecture? Why can't we have an emergent architecture and just start with nothing and sort of grow it as we need to? Here's the problem with that. What the design community says is, if you want to end up with a lorry, you don't start with a lorry. Instead, you start with a roller skate and then turn that into a unicycle and then a bicycle and then a motorcycle and then a car and then a lorry. You emerge the design as you go and kind of build on it until you end up with a lorry. That works great in design. Unfortunately, it doesn't work at all in architecture, because a roller skate does not support the same kind of capabilities that a lorry supports. The problem we're running into here is that design is all about behavior. It's the behavior of the system you're designing, but software architecture is about capabilities. What kind of capabilities do we need to support? And those are a lot harder to emerge than behavior, because behavior can sort of organically grow like a weed, but capabilities require planning. One of the things I say when people say, well, Agile means you don't really need architecture, it's like, well, it depends, like many things in architecture. It's similar to the worn-out metaphor of building something. So if I want to build a doghouse, I don't need an architecture. I need wood and a hammer and nails, and I can make a doghouse. If I need to build a 50-story office building, I need architecture. I need elevators and electricity and water. Similarly, if I'm building a simple little website to track something like a coin collection or something like that, I don't need an architecture. But if I'm building a highly scalable, highly available, high-performance web application, I have to do some planning for that to be able to support those capabilities. You can't emerge capabilities. They require planning. And this gave us some terminology that we developed in the Evolutionary Architecture book of an adaptable architecture is one that allows you to keep adding stuff to it over time. But an evolutionary architecture is one that supports internal change and evolving, getting rid of old stuff and evolving to new stuff. And emergent design, of course, is this design that gradually emerges as we understand more about the problem. This is the response to, well, Agile means no architecture. That's not true. There's not a lot of wasted upfront planning, but what this really means for architecture is the ability to do fast trade-off analysis. That's the real key in Agile architectures, is getting fast feedback loops for the analyses that you have to do. So let's talk a little bit about that. So this is a really typical trade-off analysis in event-driven architectures. I have here, this is not microservices, this is event-driven, and I have here a single database and 3 event processors, order placement, payment, and inventory. And so here's the question from an architecture standpoint. Should I hydrate the entire details for the workflow into a single contract? So in other words, I got some animations for this. I'm going to have order placement, query the database, and get everything I need to know about placing an order, and then hydrate that into a single contract, and then pass that contract first to payment, and then to inventory, and then let them write that information back into the database. That's one option. Or go back through order placement into the database is the other option for this one. The other option that I have is read from the database and just read the key and pass the key to payment and have it query the database and hydrate the rest of the information. Have inventory do the same thing, take the key and query the database and gather the rest of that information, and then have them write back to the database directly. So, which is better? Well, we need to do a trade-off analysis to see what the sweet spot is for each of these. So when I have the fully hydrated contract, I get better scalability, because one of the options there is to only hit the database once for read and then only hit it once for write and leave the database out of this the rest of the time. What is the bottleneck for scalability in this architecture? It's the single database that I have there. And so this gives me better scalability and performance if I have that fully hydrated contract. But on the downside, now I have to worry about contract management and inevitably versioning. This is one of those things that it seems like such a simple thing. Oh, we'll just version that. But now you've officially stumbled into a swamp. Because now that you've started versioning, you have to answer the following questions. How many versions are you going to support? How long are you going to support those versions? What is your deprecation strategy to get rid of versions? Is it per service or for the entire application? Do you want to support 9 or 10 different backwards compatible versions for these things? And so this can become a really, really complex thing over time that you have to deal with. A lot of architects seem to think that solving an architecture problems like solve an equation on a whiteboard, and as soon as you're finished, you can just drop the marker and walk away because that problem's solved. But everything keeps changing and moving in software architecture. So at some point, I'm going to have to version one of these things, and that's going to cause me some headaches. But the other thing this introduces, and this is one of the reasons I wanted to do this example, is something that I see all the time in modern distributed architectures, which is this idea of stamp coupling. And I want to show you how that manifests in the modern world. So this is an ancient picture. This is actually on Wikipedia for its entry on coupling. And this is so old that the worst one here, which they call content coupling, your programming language won't even let you do that anymore. That's why you have private and protected and those kind of fields in your programming language. But the age of this thing is the reason I wanted to show it, because if you can see, the next to last one there on that list is stamp coupling. This was actually named from the COBOL days, when they used to get rubber stamps made to represent their data structures, because they changed so infrequently. You could build a rubber stamp out of them and keep it around for years at a time, and you would stamp onto new requests to get things done. But this is how it manifests in the modern world. Let's say I have a profile service that has all this customer profile information and demographics in it, name, ID, email, etc. And I have a wish list service that contains wish lists for my customer, and it has everything about a wish list except the person's name that's kept in the profile service. And so I need to be able to call from wish list and gather that name from profile. But you'll also notice here that we've used JSON schema to define this contract, and we've built a comprehensive contract with all the profile information. And so when wishlist calls that contract, it just fetches the whole thing, it retrieves name out of it and uses name, and good, that's exactly what I needed. This is stamp coupling. Because at some point in the future, somebody's going to come along and say, oh yeah, I notice you have state in there. Is that the full name of the state, or is it the two-letter state code? What do you mean there? It's like, oh, you're right, that's ambiguous. We should change that to state code, which we've changed the profile service, which we've broken the interaction to the wish list service. Even though wish list didn't care anything about states or state codes or anything like that, we've now broken this communication. This is stamp coupling. Stamp coupling occurs when you pass around a contract, but one service just takes a few fields, and another service takes a few fields, and another one just takes a few fields, but that thing is brittle, because anytime it changes, it will break some of the other contracts that it's involved with, which is dangerous, and it adds brittleness to your architecture, which you want to try to avoid. So anytime you have that full contract like that, you are taking the chance of stamp coupling, because I would be willing to bet that payment uses some of the fields but not all of them, and inventory uses some of the other ones but not all of them, and so we're already tiptoeing into stamp coupling with this solution. And the final downside here is multiple systems of record. I'm hydrating that contract and passing it around, but what if somebody else updates that in the database while I've got this contract floating around? I now have to have a strategy for dealing with that, whether it's optimistic locking or some sort of reconciliation process, but that's something I have to think about. Well, let's look at the other option, which is just the key. In that case, I'm going to have a negative impact on scalability and performance, because now I'm hitting the database a lot. Order placement has to hit it. Each one of these services have to query it. They have to write back to it. And so this is going to have an impact on my scalability and performance. But I have a single system of record, so I don't have to worry about data consistency. This is implicitly implementing optimistic locking, so that whoever the last one in that writes wins in this scenario. And I don't have any stamp coupling or bandwidth or contract management issues. I'm sending the least amount of information I possibly can as part of that contract. And so this allows me to build a matrix to do this trade-off analysis. Scalability and performance is really good for the entire hydrated contract, but an issue with the rest of those, and the opposite is true over here on key data, not good for scalability, but much better on these other characteristics. But which one wins? Well, we don't know yet. Because of the second corollary, you can't just do this once. You need to have a specific situation. We've done the trade-off analysis, but this doesn't yet tell us what the answer to the question is. We need to go somewhere else to find the answer to this question. So let's talk about that. This is their law. Part of this idea of the second corollary is that there are no best practices in structural design and software architecture. Because think about what best practice means. Best practice means that anytime this situation comes up, I can just turn my brain off and always just do this, because it's the best practice. It's not even the better practice, because if it were called a better practice, that at least gives me a little bit of option to try and see if it's better than something else. But no, it's the best practice, so turn your brain off and do that thing. But you can't do that in software architecture, because all these things always pop up within a different context, all these trade-off analyses. So let's talk about who decides the outcome of these trade-off analyses. Oftentimes, it's not even the architect at all. Some people in your organization, your business, your organization, has hired you or convinced you to write some software for them. They have some concept of what value they are trying to derive from this piece of software you're building for them. And so let's say that they decide that the number one criteria is time to market. You as an architect go through a characteristics analysis and you realize that the architectural capabilities that most allow you to get fast time to market are maintainability, testability, and deployability. So that when a trade-off comes up, and I do a trade-off analysis and reach a conclusion that says, oh, well, I've reached a conclusion, the real trade-off here is performance versus maintainability. I've done the architect job here. I've done the objective trade-off analysis. Now we can feed this back to the decision maker and say, okay, here's the trade-off. I've done the analysis. Which one should we choose? We go back to, well, the things we need to support are maintainability, testability, deployability. We have maintainability. That is the one that most achieves this goal that we're trying to achieve, which is value to the organization. The point of this is these architecture decisions, because they are strategic, because they are high effort, are never made in a vacuum. You can't say always do this or never do that, because you always have to apply the extra context to it to see what's going to work or not work in a particular scenario. So let's look at some more examples of doing trade-off analysis without any kind of fancy frameworks like ATAM to do this. What this entails a lot are matrices and spreadsheets. So here's a trap to watch out for, the out-of-context trap when you're doing this trade-off analysis. So here's an architect that says, you know, I can't decide whether to use a shared library or shared service for the common functionality in my system. If I use a custom shared library, I compile time, bind that into each one of the services. Or if I use a shared service, they just call that shared functionality at runtime. You know, I can't decide which one we should implement. So what you should do, trade-off analysis to see which one's better. Now, the thing that is really super contextualized for you and your organization is coming up with this list. What are the things that are important to your organization that are going to sway you one way or the other? I mean, this is the list we've come up with for this particular scenario. And so let's look at each one of those. So heterogeneous code written in several platforms is trickier with the shared library, because in that case, I have to have a version of the library for each platform, and I have to keep those in sync and up to date, whereas for a shared service, who cares what it's written in? I'm calling it at runtime, so it can be written in all kinds of stuff and still work perfectly fine. High code volatility is also tougher for the shared library, because now every time it changes, I have to recompile it into those services and then redeploy the services. Whereas for the shared service, as soon as it changes and redeploys, everybody that calls it gets the new version of it, and so volatility is much less of an impact on the shared service. It's easier to version changes in the shared library, because I can do versions and I'm statically compiling them, so I can make sure those versions resolve correctly before I deploy it. For the shared service, I have to reconcile versions at runtime, which makes it messier and more complicated in the request to handle all of those different versions and determining who gets what version, so that's trickier. Overall change risk is less in the shared library because once I've compiled that into that library and it deploys correctly, it's probably okay, whereas you always worry about network hiccups and fault tolerance issues with shared services and distributed architecture. Performance is going to be a lot better in the shared library because it's an in-process call versus a network call, so much more performant. Better fault tolerance because, again, if it's inside that shared service, I'm not reaching out over a network that may be down to call it. And then finally, scalability. The shared library is going to be a lot more scalable because, again, I'm not soaking up network latency and bandwidth to be able to call that shared functionality. And so it looks like if you count up all the green check marks, a shared library wins. And that's the trap. Because it turns out that we have services written in 4 different languages in our ecosystem. Performance and fault tolerance aren't big concerns. We need to manage frequent changes to that shared functionality. The point of this little exercise is that when you come up with this list of criteria in your organization, the other thing you should do to them is weight them, because some of them are more important than others. Because in this scenario, even though an objective trade-off analysis seems to indicate a shared library is better, if you have this scenario, this environment, the shared library is going to be much worse, and the shared service will be much better. This is, again, you cannot universally say, oh, we should always use a shared library, we should always use a shared service. You have to do the trade-offs over and over again every time these situations come up, because there are always things that can change and trip you up. So, how do you make decisions if you have very incomplete information? This was driving one of the attendees of my workshop the last 2 days. I did a hard parts workshop, and it was driving one of my attendees crazy that architects constantly have to make important decisions based on incomplete knowledge. But hey, welcome to the job. You never have complete knowledge when you make decisions about things, or almost never. And so how do you do that? Well, here's a technique that we use to do that called qualitative analysis. Using that to iterate on your design, which eventually leads you to quantitative analysis. So let me talk about the difference between those two things. Qualitative analysis is an analysis based on the qualities of things that you can observe. Quantitative analysis is based on real data, real numbers, real results, experiments, actual outcomes for things. And we always prefer quantitative analysis if we can get it. That is by far the better because it's not a guess, it is just data and facts. But we constantly run into situations like this. I'm not sure which distributed architecture style would be most appropriate for the new accounting system, because there are at least 4 of them that seems like they might be suitable. So maybe you're lucky enough to work in an organization where you can go to your boss and say, hey boss, I have good news and I have bad news about the accounting workflow. The good news is I'm going to build you the perfect accounting workflow. It is objectively going to be the best possible implementation for an accounting workflow that can be achieved on planet Earth. That's the good news. The bad news is it's going to take me 4 times longer to build it than you'd expected and 4 times as much money to build it, because we're going to build all 4 of them and throw away the 3 that don't work as well, and we're guaranteed to have the best one. If you work in that organization, congratulations. You'll have a great career of making decisions based on complete knowledge all the time. But none of you work in that organization, nor will you ever work in that organization probably. So how do you make these kind of decisions? Well, this is where qualitative analysis comes in. So what Mark and I did in our fundamentals book is realize that when you separate architecture styles between behavior and capabilities, you can implement pretty much any behavior in any architecture style. It really just depends on how difficult it is to do that. The way these things mostly differ is how well they support certain capabilities. So that's the way we want to compare these things and do trade-offs with them. So Mark and I have come up with this scheme that we've used for a while, which is 5 stars. This actually evolved over time. It started out as just thumbs up and thumbs down like we did for the shared library thing, but we realized that wasn't nuanced enough because some of them are more than just up or down, and so we added a sideways thumb, which means in the middle, but that wasn't quite good enough, and so we ended up with 5 stars. And we really like 5 stars because each different is 20%, which is coarse enough. I mean, we didn't want 100 stars because what's the difference between 78 stars and 73 stars? That's, we're not trying to build any kind of exact metric like that. So 5 stars is nice enough. And what we did for each of these is sort of assess them based on how they compare to each other. 5 stars being best and 1 being worst. The one that's a little misleading there that we're changing to dollar signs in the second edition, cost there, a high number of stars means good, which means inexpensive, which we realize is confusing, so we're changing that and inverting it to dollar signs. But what this allows you to do is to do more of an apples-to-apples comparison between the capabilities. Because these are the sweet spots for all the capabilities in these different architectures. And so now I can say, okay, well, I understand what each of these does best. Now let's go back and see what our goal is for this particular system. It's maintainability. Which of these supports maintainability, deployability, and testability better? It looks like microservices does, so that's the one that we should use to implement this. Or maybe, if there's still some uncertainty, you pick the top 2 with a qualitative analysis and do some design on those and do a little further analysis, but this is a way to narrow down some of those kinds of questions. One of the things that we did in the Hard Parts book with Pramod Sadalge, one of our co-authors, is do a qualitative analysis for all these different kinds of databases. This is one of those things that many architects have to make informed decisions about these days, and so we did that exact same kind of analysis here with relational databases, really easy to learn, mixed, balanced read-write priority, really good programming language support, but really bad at availability and partition intolerance. Key value databases are more read-heavy than write-heavy, really good at availability and partition tolerance, but way less good at consistency than relational databases, so you can kind of see how these compare to one another. Document databases have, again, read priority, but the same kind of consistency as we saw before, but not as much scalability. Columnar databases are designed to be super scalable, so you get really good write performance, but consistency is really challenging in those databases. Graph databases are really good at graph-shaped data rather than relational set-based data, and so it's learning how to program that is more complex than SQL, so the programming language support's a little trickier. And then finally, new SQL databases, which are things like VoltDB or ClusterXDB, trying to kind of replace some of the semantics with the relational databases with a fewer moving parts. So they balance read-write priority and have a fairly median view of the rest of these. Another example of doing this kind of qualitative analysis on databases to see, okay, given the problem I have, the relational database is no longer the golden hammer solution to every problem, and this gives you a way to compare them. And lastly, we did the exact same thing for transactional workflows, or sagas, in microservices speak. We ended up modeling all 8 different possibilities of these different kinds of sagas, and then did the exact same kind of qualitative analysis on these, with looking at how decoupled it is, how simple, how responsive, and how scalable it is, depending on the settings over there, those 3 columns. And now if we go back to our decision criteria and say, okay, what was the thing that was really important here? It was maintainability. Well, the problem is I don't have maintainability here as one of my criteria because it turns out it didn't float to the top as much as these others did, but there's one that's a good proxy for that, which is simplicity. So let's choose the really simplest architecture, the easiest one to understand, and that gives us faster time to market. It's easier to maintain, it's easier to test, it's easier to deploy, and so this allows me to narrow those criteria down using that qualitative analysis. Once you have done that qualitative analysis, you should then switch over to quantitative analysis. You've already objectively defined what you want out of your architecture, so build an architectural fitness function to actually validate that. You've already done the hard work, which is the objective definition part, and now this serves two purposes. One, it helps you govern important things in your architecture, because pretty much by definition, your decision criteria for choosing this architecture is an important capability in that architecture. So if you've chosen maintainability, wouldn't you like to check and see how well you're doing on maintainability if you chose this architecture? And that would be how many tickets are being submitted, how many errors are showing up, how fast are things being fixed. Those are all measures of how maintainable your system is. And this lets you objectively measure the things that you qualitatively guessed at. But the second good reason for this, of course, is it helps you over time get better and better at qualitative analysis, because you can see how it works out and how it resolves. Okay, here's another scenario. Model relevant business use case scenarios to identify trade-offs. Here's the problem. I wonder if we should use a single payment service or a separate service for each payment type. This is the question that motivated this. Maybe this is trickier than we thought. This is on that spectrum of architecture versus design. So one of the ways to solve this problem is to model some things that we think are likely to happen in this architecture. So we have a single service and we have shared services. Okay, let's model some business use cases to see what they would look like. And the first one we'll do is update credit card processing. So if I need to update credit card processing on the single service, that means I need to change the code and change the database and probably test everything, because I'm changing code inside that monolith. Versus over here in the separate services, hey, decoupling is great. Change one place, nothing has to affect the other services, and so separate services give you better maintainability, testability, and deployability. The second scenario, add a new payment type, like reward points. Okay, we'll add reward points over here to the single service, which means I've made a change to that code base, which means I need to test it and probably make sure the database is still working correctly and all that sort of stuff. Over here on the right, hey, microservices are awesome. Spin up a new service, decouple, no effect to the other services, and so separate services definitely give me better extensibility. All right, let's do one more. Use multiple types for payment. Okay, well, we can add reward points over here on the single service, and now it's easy to resolve, just add all of it up. It's an ACID transaction in a single database, so nice and clean and easy. We can make sure that all that coordination worked correctly. On the right-hand side, now I've got to have coordination between these nominally independent services to coordinate mixing and matching this payment thing, which means I'm going to need some sort of orchestrator, either an explicit one or an implicit one. And now I'm trying to do transactions across services in a microservices architecture, which is possible but frowned upon. You generally don't want to do that as much as possible because it creates all sorts of interesting complications. And so the separate services here are much worse at performance and data consistency, which will be real headaches for us if we end up implementing the solution on the right. So which one should we choose? Well, despite the headaches, the one that most supports our goal are the separate services with maintainability, testability, and deployability. But see the benefit of going through this analysis. Now I know what I've got to work on, what the weak points of my solution are, because I've gone through that analysis and said, what does it do good and what does it do poorly? And now I can help make that right. And so ultimately, to answer the question I posed earlier, while this may seem like a really simple thing, this is a lot closer to an architecture level decision than it is a design decision, because it does have interesting side effects. And sometimes you can't really tell that until you've done some of this sort of analysis. And finally, I'll leave you with a bit of advice here, is to avoid over-evangelization for a particular solution or technology. I used to do a keynote several years ago called, "Why Does Yesterday's Best Practice Become Tomorrow's Anti-Pattern?" Because it seems like that always happens, and a lot of times in architecture, you'll make the correct decision now, but then the entire ecosystem slowly changes and evolves, and 6 months or 2 years from now, that solution is no longer correct because enough of the world around it has changed, and if you were the evangelist for that, you always end up looking bad. And there's another danger, which is this. You have a software architect that falls in love with a particular kind of architectural solution. We should always use publish and subscribe broadcast messaging using topics rather than queues, because it supports architectural extensibility and evolutionary architecture better. And here's what I mean by that. If I'm building this interactive workflow using individual queues and I want to add a new consumer, that means I have to add the consumer and I have to add a new queue and I have to change the bidder and I have to build a new contract. If I'm just using topics, on the other hand, I needed to add a new consumer. I just subscribe to that topic. I don't have to change the topic. I don't have to change the bidder. I don't have to change anything about the contract. This is why I love topics so much in event-driven architectures, and all these developers are like, wow, you're right, that's awesome. We'll make that a best practice here in our organization and always do this. And then the narrator's voice comes in and says, meanwhile, a little while later at this organization, oh, wait a minute, I can't create separate contracts for each one of these services. And guess what? We have stamp coupling all over the place here, because now I'm sending these big contracts and people are snipping little parts out of it, and now it's getting brittle. That's a real headache. And oh, we just had a security breach because everybody can see every bit of what's in that contract, and some of them shouldn't be able to see it. There are laws about this sort of stuff, GDPR, and there are HIPAA laws in the US about information that should not be pieced together. And if you're sitting around these giant contracts, it's easy to fall into that trap. And, oh, well, you know, we'd really like to do auto-scaling, but you can't. Because to do auto-scaling, you need queues because you need queue depth, and topics don't have a queue depth because everybody just subscribes to the topic, and you can't manage one single consumer versus the other. And so now we've built a bunch of situations that we can't manage. So this is why evangelism is dangerous, and that you keep having to do the trade-offs every time this decision comes up, because everything in software architecture is a trade-off. And the real trick in software architecture is find a way to get fast feedback on your decisions and a way to do trade-offs so that you can get fast feedback and iterate on your design to get to a better place faster. That's it. Thanks very much.